which is Cm, right? So imagine, you've got big N here of these wave functions, and you multiply each one, psi I by Ci. You do that for all capital N of them and sum them, and you'll get this general wave function, okay? Which goes here. Now, if you want to know, well, what's the value of Cm here? Well, you bra it with psi m, and to find what Cm is, your component, your coefficient here, right? So these wave functions here, you can look at them as, well, sort of like this, as orthonormal vectors. Now, this term orthonormal, what does that mean? Well, again, I'm hoping you've done some vector calculus. I will teach a course on this, on vector calculus. But orthonormal, what does that mean? It's two words put together and shortened. So orthonormal is shorthand for orthogonal and normalized. Orthogonal means that so these two wave functions. Hold on. Here, these two wave functions are said to be orthogonal if the integral here is 0 when m and n are different, okay, and they are equal to 1 when m and n are the same. That's what orthogonal means. Well, hold on. No, that's not quite true. Orthogonal is when m and n are different, this integral is 0. And when m and n are the same, is non-zero. Now, normalized means that when m and n are the same, this integral is 1. Okay, normalized. So orthogonal and normalized. So just for short, orthonormal. So these vectors here are orthonormal vectors. So if you take the overlap integral of two of them, you'll get either 0 or 1. Right? You get the delta function. Okay, which is similar to these vector unit vectors. I mean, but now you're thinking of wave functions as unit vectors. All right. Now, next concept. The idea of projection. Imagine now, imagine a plane coming out of the board as my hand's moving, and then imagine up here a light, and then you've got a vector. Imagine like an arrow, like this, and then the light's up here, shining down, and you'll get a shadow on this surface, on this plane, the shadow of this length. This shadow here, this vector that you get here, is called the projection of this one. Right? So think of a projection as a kind of shadow, if you like, onto a space, in this case a plane. A space of smaller dimensions. So you can project this vector into this one. So this vector here is the projection of this one. Okay? So in a sense, you can say if you take this bracket, what you're getting is, so here's your generalized wave function, okay, your superposed wave function, and then you bra it with this wave function psi m. Now the result you get is Cm. We did that up here, okay. So this is, in a sense, the component you get. You can't really say length. This is like in real space with real numbers, but these are complex numbers. so this number here is the component you get when you, in a sense, project this. So this general superposed vector, that would be this one, correspond to that one, and this vector, the projection of that one, is the component here along this direction, and this direction here is psi m. Okay, so that vector there is psi m, and this general vector here is just psi. And so how much, in a sense, how much of psi m do you have? Well, its component will be Cm. So you can think of brackets as being useful for projecting. So you can, in a sense, you're projecting your psi in the direction of psi m. That's probably the essence of it. Okay, so when you want to know what's the component of psi m in your general sum here, superposition, you just bra it. So projecting and braing, effectively same thing, right? Now this general vector here, this superposed vector psi, over time it will usually change because under the influence of the Schrödinger equation. The general Schrödinger equation is time dependent. There's a d psi by dt in the Schrödinger equation. So this general superposed wave function will vary, will change with time. Okay, so if you're looking on this wave function as a vector, so that means these components here will change with time, and so your vector in vector space will be changing its direction. Okay, so expect this to be changing with time, because of the because it's subject to Schrödinger's equation. Now, if we're going back to the thought experiment before with the box and the trap doors, and they're all falling, and so you then your psi function then has these psi n parts to it, and then if you actually see the particle in one of those volumes, say in the little nth volume, then that means immediately all the other wave functions and all the other n-1, little n, or big n-1, they all suddenly go to zero, because you now know that the particle is in the little nth volume, and this phenomenon is called collapse of the wave function. Now it's highly controversial, as I was saying in the previous session or so. The problem of measurement, interpreting what is a measurement in quantum mechanics, is still highly controversial. There's a huge amount been written on this topic. What constitutes a measurement in quantum mechanics? And there are various paradoxes. One I'll be mentioning quite a bit later is the famous Schrödinger, because Schrödinger formulated it, the Schrödinger cat, CAT, paradox, and that comes out of using the standard answer to what is a measurement in quantum mechanics. So in a sense, your wave function is evolving away when it's undisturbed, and as soon as you make a measurement, the wave function collapses into another wave function. So a lot of people are not happy with that at all. They don't like that. They say the measuring apparatus is itself a quantum mechanical object, and therefore the measuring machine and what is measured, they're all just a quantum system, right? So the whole thing should be subject to quantum mechanics. So why do you get this collapse? Doesn't make sense. So it's a paradox. It's a problem. interpreting what a measurement is in quantum mechanics is one of the big headaches of quantum mechanics. But I'm jumping up to like first year master's level, so I'll sort of leave it at that.